Hi there, welcome to this practice run of my master's seminar presentation at the Working Group for Nonlinear Optimization in the Mathematics Department of TU Darmstadt. This presentation will be about the Quasisecant method, which is a generalization of the classical subgradient method to non-convex, non-smooth optimization problems. So why am I recording this video? This is, first of all, for you, the interested listener, to get a summary of a interesting paper, which this presentation will be about. And secondly, of course, this is a good practice for me, such that my actual presentation next week will be better. So let's get started. So this will be our today's agenda. We will start by a short introduction of the literature regarding this topic. Then we will discuss some preliminaries which are necessary to understand the basic mathematics behind this method. And then we will introduce quasisecants, which are the main ingredient to this novel method and their respective properties. After that, we will look at the problem of finding descent directions, meaning directions of descent for this optimization problem and the step length to these directions. After that, we will come to the main part, namely what is the quasisecant method and how can it be employed to find something called H delta stationary points and actually how to find real stationary points. In the end, we will have a look at some of the initial numerical tests that were made, and we will give a short conclusion in the 7th section. So let's get started. This presentation is, roughly speaking, a summary of paper 4, which introduced a new method for solving non-convex, non-smooth, unconstrained optimization problems of a locally Lipschitz continuous objective. The main idea behind it is the notion of quasisecants, which was introduced in this other paper. And the objective is to find a compromise between two of the most highly regarded or frequently employed methods right now, namely on the one hand the subgradient method and on the other hand the proximal bundle method. So the subgradient method, as you might remember, is some generalization of the method of steepest descent to non-smooth problems and just replacing the gradient with subgradients. So it's easy to implement, it has cheap iterations, but in general it has a low performance because it has the same problems as the method of steepest descent. Namely, you might get some oscillation or very short steps, such that you don't get the convergence properties you might want. However, it's suitable for large-scale problems. It's very, very common for deep neural networks. But it's only applicable to convex problems, just like the bundle method, which builds up a model of the objective function consisting of hyperplanes, and then this model is minimized and it gets improved as you iterate. So it's rather complicated and has costly iterations, at least compared to the subgradient method, but it generally has high performance for smaller problems and is unsuitable for larger problems. So the idea is now to find a compromise between those two methods of easy implementation and performance and high performance, and also generalize generalize the convergence to non-convex problems. So now we will formulate a problem and make some notation and prior knowledge available to you. Now, what is the aim? What is the aim of this algorithm? It is to find a local minima of this locally Lipschitz function f on a unconstrained domain in R to the n. So the whole space. For notation, for readability and simplicity, we will omit the subscript 2 at the Euclidean space, and we will denote SR. We will denote the sphere of radius r around the origin by SR. We also will denote a ball of radius r around a point x by BR of x. Now, we need the notion of local Lipschitz continuity, and this is a little bit technical because these definitions might seem very similar, but they are not. So locally Lipschitz continuous in or at a point x means that you find some Lipschitz constant L and a radius of a domain around this point x of a neighborhood, a delta, such that the Lipschitz inequality is satisfied around this point and always including this point x. In contrast to that, local Lipschitz continuity around a point x means a generalization of this, meaning that you don't need the point x, but may replace it with another point in this neighborhood. So it is in fact a more powerful notion of Lipschitz continuity, of local Lipschitz continuity, compared to the first one. Now, if the objective, if the function is Lipschitz continuous around every point in the domain X, then we call the function itself locally Lipschitz continuous. We also need directional differentiability. So we distinguish two kinds of directional derivative. First, the usual one, namely you have this difference quotient with t approaching 0 in the direction d. If that exists for all directions d, then we call the map f directionally differentiable in X. And if the same definition holds, but not with a fixed point X, but with for every sequence approaching X, then we call it generalized directional differentiable. So it's again a real strict generalization where this slant, this distortion vanishes as y approaches x. And now this also has to exist for all directions for the map to be generalized directionally differentiable. If both of them exist and coincide, we call the map regular in that point. Now for the next definition, we need this result to make it useful in some sense. So Rademacher's theorem is one of the central theorems of non-smooth analysis, and it states that if you have a locally Lipschitz continuous function on a non-empty open set, then it's differentiable Lebesgue almost everywhere, meaning the point the set of all points which are where the function is not differentiable is a Lebesgue null set, so a subset of a measurable set with Lebesgue size 0. Also very central for this presentation is the notion of subdifferentials. So for a convex function, we say that a vector is a subgradient if the subgradient inequality holds, and the set of all subgradients is called the subdifferentiable and denoted by del f of x. For a visualization, you can look to the right and see the absolute value of x, where you have these hyperplanes as underestimator of the function, and that's exactly what the subgradient inequality demands from G. Then we also have the B subdifferentiable from B standing for Bouligand, and it means that you have a sequence of points in the set of differentiable points which approaches some point x. And then looking at the corresponding gradients, they have to converge to G. Then this vector is in this set del B f of x. So for the absolute value, this would be the set only containing -1 and 1 in the origin, because it always depends from which side you approach the origin, but there will always be just these two possible vectors in that set. The Clark differential takes the convex hull of the set and can be understood to be the set of all plausible derivatives in a point. So the Clark differential is -1 everywhere on the negative part of R, and +1 on the positive part of R. And in the origin, it's the whole closed interval from -1 to 1, which somehow makes sense because it's the set of all plausible derivatives in that point. So if you ask somebody what is the derivative in that point, anything apart from a value between -1 and 1 would be very unintuitive. So why is the Clark subdifferential so powerful? It's because it's a real faithful generalization of the classical derivative and the subdifferential, meaning that it coincides with the classical subdifferential if f is convex, and if f is smooth, it only contains the actual derivative, so the gradient of f in that point. It also has this nice property, which is really very close to the notion of continuity in the real case with this epsilon delta criterion. But here we are dealing with a set valued map. So here we have a very similar inequality, but now it's an inclusion, and just states that if you don't modify the input too much, the output still doesn't change significantly. So for all epsilon, you can find such a delta depending on epsilon, such that this ball of inputs doesn't produce an output which is outside the actual output plus a small ball which extends this set. So it's really a continuity notion, and yeah, this has to be removed. And now, if 0 is element of the Clark subdifferential, then we call that point Clark stationary. So in the case of the absolute value, the only Clark stationary point would be the origin. And this, in fact, stays a necessary condition for local optimality, and for convex F, it is even a sufficient condition. So very, very similar to the smooth case. Now, what are quasisecants in the first place, and for what can we use them? So to start, we derive this consequence of the upper semi-continuity of the C subdifferential. So take some direction S in the unit sphere and a length h. Now take the union of all Clark subdifferentials on that line segment from x to x plus hd. Then this set is also upper semi-continuous. That is an immediate consequence from the upper semi-continuity of C, because this line segment itself can be embedded into a ball And then if h approaches 0, we have exactly the same argument as in the definition of upper semi-continuity. So we have this identity here. Now, to the most important definition of this presentation, a vector V is called quasisecant of a locally Lipschitz map at a point x in a direction d with length h if the quasisecant inequality and the approximate subgradient condition hold. So the quasisecant inequality should be familiar to you in the sense that it is very reminiscent of the subgradient inequality, but it only has to hold for this one point which has distance h. So we have the subgradient inequality for this one length. And you can see a visualization of this at the graph on the right-hand side. So we just demand this to be an underestimator for that point. So the hyperplane doesn't have to be above the graph of f everywhere. And the approximate subgradient condition states that V must be in that union on the line segment of subdifferentials, but not quite. There is some tolerance, which is denoted by this Landau notation, meaning that for each x, there exists a map G, for example, that vanishes as h approaches 0. So this definition is actually only interesting for h approaching 0. And for a quasisecant at a point x in direction d of length h, we write v of x dh, and note that this notation has to be read with caution because the quasisecants are not unique, meaning that the quasisecants are actually a whole set qh of x of quasisecants with length h at point x in any direction, and therefore is not unique because the set generally contains more than one vector. And its closed convex hull will be denoted by wh of x, and the set of all limit points of quasisecants, meaning we have a sequence of directions and a vanishing sequence of length. And then we have this sequence of quasisecants which are associated to these parameters, and they should converge to W. Then all these W's are in the set Q0. And then again, we take the convex hull and get W0. As Q0 is already closed, we don't take the closed convex hull, but only the convex hull now. So by upper semi-continuity, we get that for any x and length h, we find a suitable epsilon such that this set QH of x is actually not much different of the Clark subdifferential at x. We just have to add this ball of radius epsilon. So how can we see this? Well, the identity in the middle immediately follows from the fact that here we have these line segments in the unit sphere, and we take the union over all of them, so we can summarize them to the unit ball around 0. And then for the inclusion, we use again upper semi-continuity. So by reminding ourselves that the Clark subdifferential is bounded, we also get that QH of 0 is bounded, and therefore WH of x is compact because it was the closed convex hull. And therefore, we also derive the compactness of Q0 at x. This should be an x, because it's already bounded, and now taking the closure means that we are compact since we are in R to the n. And by extension, we also derive compactness and convexity of W0 of x, because now we also take the convex hull by definition, and therefore we get both these properties. Now, how can we get sure that we aren't talking about the empty set all the time? For that, look at Lebourg's mean value theorem, which states that if you have a locally Lipschitz map F, then there exists for each pair x and y of points, there exists an intermediate point on this line segment such that the secant through those 2 points has the slope which is element of some of the Clark subdifferentials on that line segment. So this is the intuition behind this theorem. So what can be derived from this for our purposes is that quasi-secants exist for locally Lipschitz continuous map, even without this Landau term, which gave us this small tolerance. But the proof of the theorem doesn't give a constructive way to find quasi-secants, because it's only an existence theorem and it doesn't have a constructive proof. So what we do is we relax these 2 conditions to the conditions we had before in our definition of quasi-secants, to allow for efficient computation of quasi-secants, at least for convex map and DC functions. DC functions are functions which can be represented as a difference of 2 convex functions. So in the case of convex F, we can replace x and y in the previous identities and can see that any such subgradient v in x plus hd is a quasi-secant at x. And it even holds the following assumption, which we must demand in the sequel, which states that this residual term OXH vanishes locally uniformly in the location. What this means is that for each point x, there exists a small neighborhood around it, such that these residual terms, which are functions that might differ in x, but now they must converge at least locally uniformly with h approaching 0 to 0. So it's really a local uniformity statement here. Now we will have to do some prove some a sequence of propositions to in the end prove the convergence properties we are striving for. So take some point x and some epsilon, some positive epsilon. Then we have a number t, a positive number t, depending on those 2, such that we have this chain of inclusions for all h in 0 to t. So by definition, WH of x and this set on the right-hand side is convex. So if we show the inequality from the very left to the very right, we are actually done, because then we can take the convex hull, the left one becomes the middle one, and the right one doesn't change. And you might say, okay, we still have the closure, but the closure doesn't add to the diameter. So if we reduce to epsilon over 2, for example, then the closure doesn't bridge this epsilon over 2. So it really suffices to show the inequality, the inclusion from the very left to the very right, and omit the middle part. It is the first inclusion is, you could also do it differently, but the first inclusion is really obvious anyway by construction. But this inclusion from the very left to the very right was exactly what we already showed in remark 3.3 by upper semi-continuity. So now we have the strongest statement where we have to assume assumption 3.6 to hold, but now we have this chain of inclusions with x being replaced by y, where y only has to be in a ball around x. So it's really a stronger statement apart from this additional assumption we have to suppose. So as in the proof before, it again suffices to show this inclusion. Now, from the definition of the set QH, we immediately see that it is just a subset of the union over all directions on the unit sphere. And using the assumption, we can control this residual term, meaning that we for all epsilon, we find a delta 1 and a T1 such that this residual term is bounded by epsilon on this neighborhood of y's and h's. So we can rewrite this on top by adding this general term, which is outside of the union and has radius epsilon. Now we again use upper semi-continuity for the following inclusion, and now we can use so we have again a epsilon delta and t statement with this inclusion derived from the upper semi-continuity, and using these two inequalities, these two inclusions, and taking delta to be the minimum of both delta 1, delta 2, t being the minimum of t1, t2, we have both of these identities and add simultaneously. And then that's the statement we wanted to show. Now, proposition 3.9, note that now we have subscript 0. For locally Lipschitz F, we have again a chain of inclusions. So the first inclusion is really by definition because this is just the convex hull. Therefore, this inclusion is trivial. And the second inclusion again reduces to the first one because we have convexity of that set. Convexity is exactly what differentiates those two sets, because then if we have shown that this is a subset of that, we just take the convex hull, this becomes this, and the other one stays invariant, and then we are done. So this is all we have left to show. So for the proof, take a sequence of directions and a vanishing sequence of length, and consider these sequence elements, which we rewrite in the following way, just by using the definition of this set. Then we know that the residual term vanishes, and we have upper semi-continuity. So this inclusion is just derived from the definition, because here we have x plus essentially, it is essentially a ball, because we have this direction dk and all the length between 0 and hk. So we can make this set larger by taking more inputs, namely the closed ball of radius t. Then we trivial get all of the length into that set. And now this set becomes smaller and smaller when hk vanishes, and then we can use upper semi-continuity to see that it actually converges downwards to the case where only x is the input. And then d doesn't even matter anymore. So we can conclude that the sequence of quasi-secants has a limit that is in the Clark subdifferential. And therefore, we showed this inclusion from the one side to the other side. Now, for our, what I think will be the last proposition, if I remember correctly, we have for locally Lipschitz f this inclusion, this inequality, and if f is additionally directionally differentiable, we have this other inequality. So note that the directional derivative is defined because we assume directionally differentiability, and this is somehow interesting to us because if we assume regularity, we get a identity. So for the proof here, a short reminder what we want to show. We know that by construction, W0 is a subset of the Clark subdifferential. This was shown in proposition 3.9, and therefore this inequality is obvious because we're taking the maximum over a larger set. Now the rest of the proof is a little bit lengthy and is a implicit consequence of page 27 in combination with theorem 2.5.1 of 6, which is Clark's book, and there the definition and the statement of the generalized directional derivative are exactly opposite. So here the theorem shows that our definition coincides with the statement instead of vice versa. So it's just the other way around, but the proof is in this book. And the second claim is also very technical and surpasses the time restrictions of this presentation. So let us continue with the implication of it, which is actually relevant to us. Namely, as I just mentioned, if we assume regularity of f, then this implies that the Clark subdifferential and the set W0 actually coincide. So why is this true? Well, by definition of regularity, we have the equality between the generalized directional derivative and the usual directional derivative. And by the proof of proposition 3.10, we know that we have this identity where the only difference is the set we are taking the maximum over. So why does this imply that also the sets must be equal? The other way around is obvious, but why also follows from this identity that the sets must coincide? Well, assume they don't, meaning there is a point in W0 which is not in the Clark subdifferential. Then by convexity, we can use the separating hyperplane theorem. So the Clark subdifferential is a convex set, and we have a point which is not in there. So we can cut a hyperplane in between them with strict inequality. However, since we still have the inequality, we now get this chain which becomes a strict inequality, which is a contradiction to the equality we derived before. And therefore, this cannot be the case, and these sets actually have to be the same. So how do we find descent directions for our quasi-secant method to then employ a line search procedure? Consider the following algorithm. So we are given a point x and a parameter c1 between 0 and 1, a length h, and delta as parameters. So select a direction d1 in the unit sphere and compute a corresponding quasi-secant. Now set v1 bar to v1, which will be this will be some cumulative quasi-secant which takes into account all the sub-problems we solve over the course of this algorithm. So right now it's rather uninteresting, but it will become more interesting. Now for in each iteration, solve the following problem. This means that we want to find the lambda such that the distance to the origin on that line segment sk is minimized. And then we call this lambda k tilde, and we define the aggregate quasi-secant to be exactly that point on that line segment. And we stop this iteration if the quasi-secant is small enough. And if that's not the case, we compute a descent direction, which is just the normalized negative of that aggregate quasi-secant, and we stop if this direction yields a sufficient decrease, meaning the amount we reduce the objective must be larger than this linear term. So we, starting from the point x, we have a line going downwards, and we have to find a point which has a objective that is lower than the one of this line. And then we iterate, so we compute a quasi-secant at that point and update our vk to vk plus n and say that that's gets assigned the quasi-secant, and the role of our vk tilde will be taken by the old aggregate quasi-secant. So how do we know that this algorithm stops? That's exactly the statement of this proposition. So if the set WH is bounded by some finite d, and delta is between 0 and d, and C1 again is between 0 and 1, then algorithm 1 stops after a finite number of iterations, which can be bounded by this term with this constant in it. And the proof idea is, the whole proof can be read again in the paper, in the main paper, which this presentation summarizes. But the idea is to negate the condition in line 1. So say we don't exit the loop with 9 with line 9, but line 7. So we negate this inequality and show that then at some point 7 will kick in. So now that we saw that we can find descent directions after a finite number of iterations and a really easy to solve convex subproblem, with this lambda term, we now want to introduce the quasi-secant method itself. For that, we define what a H delta stationary point is, and that's just that the set WH has norm less than delta. Now, from proposition 3.7, we know that for x and positive delta, there exists a T such that this inclusion holds for all H smaller than T. Now, if we now assume X to be H delta stationary, we can execute a triangle argument. So we know that WH is really similar to delta to the Clark subdifferential, and the difference is bounded by epsilon in some sense. And we know that the distance of WH to the origin is also at some point lower than delta. Therefore, in the worst case, we have that the Clark subdifferential has a distance of epsilon to this W set, and this itself has a distance lower than delta to the origin. Therefore, we can make a triangle argument and say, okay, the Clark subdifferential isn't too far from the origin itself, namely at most epsilon plus delta much. So H delta stationary points become approximately stationary with decreasing delta and epsilon. So for small h in that sense. So how do we find such points? Now, in addition to C1, which we considered before, we now also have C2, which is a constant bounded above by C1. And again, we have delta, a positive delta, and H. So this is just the usual line search procedure you might be familiar with from nonlinear optimization. So we apply algorithm 1 to get the direction. If the direction is small enough, we terminate. Otherwise, we compute the largest step length possible such that we are under this hyperplane, this line. So we have a sufficient decrease, and then we update our iterate and do this over again. And again, as before, how do we know that this terminates? Well, this theorem guarantees that algorithm 2, if f is bounded below by some f infimum, then algorithm 2 produces a H delta stationary point, and the number of iterations is at most this quotient. So for the proof, we will do a proof by contradiction. So assume all of the iterates to not be H delta stationary, meaning that this minimum is larger than delta for each iteration k. Then algorithm 1 had this two exit conditions, and the first one doesn't kick in, so the second one must be the one where we terminate. So from that, we get the following inequality. Now we can use that the step lengths are always larger than h, and can therefore plug this into this inequality. Now, combining this with the fact that the condition in line 7 never kicks in, we can plug this inequality into one before, and what we see then is, if we increase k, then this term diverges to minus infinity. However, we are bounded below by f infimum, so that's a contradiction. And rearranging this inequality actually gives exactly the bound we wanted to show. So we get finite convergence of algorithm 2. And how can we take this a step further to get stationary points, not H delta stationary points, but actually stationary points? Well, we take some tolerance mu, some positive tolerance mu, and start at some initial point and define sequences H and delta that vanish. Then if H or delta is smaller than mu, meaning we are approximately stationary, then we are done. Otherwise, we iterate over and over again, algorithm 2, for this H, K, and delta K, which becomes smaller and smaller. And we doing that, we get solutions xk. So we get hk delta k stationary points for each of the iterations of this algorithm we execute. How does this give us some kind of convergence? So suppose f to be locally Lipschitz and fulfill assumption 3.6, which was this uniform convergence of the residual term. Now further assume that the level set of the initial iterate is bounded and that the tolerance in algorithm 3 is 0. Then every cluster point of the sequence of iterates is Clark stationary. So if there's some convergent subsequence, then the limit point of that must be Clark stationary. So by local Lipschitz continuity of f and the boundedness of the level set, we immediately see by the standard arguments of analysis that f is bounded below. Now we apply the previous theorem 5.2 to get that each of these stationary points is found after a finite number of iterations. And since they are HK stationary, we get the definition of being HK stationary. So this inequality. By this sufficient decrease condition, we also know that we have a monotonic decrease so that all iterates remain in that level set from the first iterate. So now we have a sequence of iterates in a bounded set. Now all your bells should be ringing because that's Weierstrass theorem, which is looking around the corner. So we find a subsequence of iterations that it's such that its corresponding iterates converge to some limit point x star. Now summarizing this, so just boiling down this inequality before to this subsequence, we get this inequality. And now we can apply proposition 3.8, which was one of these technical propositions from before. So what is important about that is that in a neighborhood of that limit point of radius eta, we are actually more or less within the Clark subdifferential for any length that is small enough. So keep that in mind. We know that xki converges to x star, so there is an index such that all the iterates from that point onwards are within that ball of radius eta. And we know that both delta k and hk vanish. So we also have a index such that delta k is bounded by epsilon and hk bounded by eta. Now we also need an index I1 such that this the subsequence index ki is larger than k0. So we do this translation from subsequence to sequence. So it's, yeah. And then we take the maximum of I0 and I1, and taking the maximum, we can combine all of these properties, because now we are actually far enough down the line for all of them, and use this for and plug it into the inclusion from above, to then deduce this inclusion for all the indices that are far enough down the line, meaning that now we replace h by hki, and we have that delta k is smaller than epsilon. So we get this inclusion from being far enough in the iterations, and this consequence of proposition 3.8. Now we combine this inequality with the inequality from before, namely this one applied to the subsequence. So here, summarizing, this one plus this one, and we get the result we are looking for, because delta ki minus 1 is bounded above by epsilon, and here we are also bounded above by epsilon. So using that this set is subset of this Clark subdifferential up to some tolerance epsilon, and we have this inequality also for delta, which is smaller than epsilon. We have again a triangle argument, if you want, that the norm of the Clark subdifferential at our subsequence limit point is bounded above by 2 epsilon. Now epsilon was arbitrary, so we know that that's actually a 0 right here if we take zeros small enough. And therefore 0 must be in the Clark subdifferential, meaning that this limit point of the subsequence is actually Clark stationary. So since this subsequence was arbitrary, we know that every convergent subsequence must have a Clark stationary limit point. So how does this translate into practice? So for that, the paper we considered throughout this presentation took a set of really common common problem instances in the literature for general non-smooth problems, and also for large scale problems, and compared them on the basis of one fixed starting point and 20 random starting points, which were homologated between those two methods. And the solvers that were compared were the subgradient method in two different versions. In one case, with some vanishing step size, but it's as you can see, it's a little more involved than a vanishing step size, because it vanishes and then at some point after 25,000 iterations it kicks up again, and then it vanishes again. So it's kind of a wavy kind of step length formation. And the second version is more or less a constant step size variation. So for the first 10,000 iterations, we have the step size of 0.005, and after that 0.0001. Then we what was considered was the proximal bundle method from paper 8, and the Quasisecant method for this set of parameters. And we use this tag to compare them. And what is the metric used? Well, they considered the problem to be solved if the objective value found doesn't differ too much from the known local optimum, from the nearest known local optimum, in the sense that this inequality must be satisfied for some accuracy kappa. And for the visuals, they took performance profiles. So they measured something like the CPU time or the function or subgradient evaluations. Denoted this by TPS for problem P, solver S, and then took this quotient, and it's kind of a underperformance factor in the sense that it's always greater than 1 and only 1 if this solver was actually the best one for that problem. And then you look at these underperformance factors, which are larger than 1, and look at how many of the problems were solved with a underperformance factor of at most tau. Meaning what you want is, in that graphic here, you want this curve to be starting very high up, because that's the share of problems where this algorithm is the most efficient among all of them. And if you want them to rise steeply. So in this picture, you can see that the proximal bundle method is for more than 80% the best algorithm, and the Quasisecant method is only optimal for about 10%, but really doesn't have too much of an overhead. So the underperformance factor is very controlled compared to the subgradient methods, which have really a slow increase in slope, meaning that they have high underperformance factors around 6, 7, 8 times the most performant method. For large scale problems, R had to be logarithmized for visual reasons. Yeah, but I will provide the visuals from the paper in the end for you, but you can more or less summarize them as follows. As you know, we determined we chose this kappa accuracy, and we also chose the metric we counted, so function evaluations, subgradient evaluations, or CPU time. It actually turns out to be not that relevant how you choose them, because the results don't differ too much between those two arbitrary, in some sense, choices. And therefore, you can really summarize it roughly with this table I compiled. So for minimax problems, which will be presented in figures 1 to 3, we see that the Quasisecant method is better than the subgradient methods and bounded above, so it's outperformed by the proximal bundle method. And that's more or less also the case for the success rate and also for generic non-smooth problems. However, for generic non-smooth problems, the success rate is actually on par with the proximal bundle method. But again, it's really dominating the two versions of the subgradient method. For large-scale problems, however, the Quasisecant turns out to be the most performant solver. So it's even better than the proximal bundle method with respect to the efficiency, so the convergence speed, but also the success rate, so the share of problems that could actually be solved with regard to that inequality here. So really, for large-scale problems, Quasisecant method is very powerful, And for the other ones, proximal bundle method might be the method of choice, but the quasi-secant method is arguably larger, easier to implement. So this is more or less also our conclusion. So the paper generalized the subgradient method to unconstrained, non-convex, non-smooth optimization problems. The algorithm only contains simple procedures as minimizing a convex objective or this line search procedure. What's actually the most difficult aspect of it is finding this quasi-secants, which is only shown right now in these papers for convex problems and DC functions, so difference of two convex functions. So that's the hardest part of it. We have shown global convergence to stationary points, starting from H-delta stationary points to Clark stationary points. And the initial numerical tests indicate the superiority over the subgradient method in all of the problem categories we considered, and the proximal bundle method, at least for large-scale problems. But I think it is safe to say that there is further testing necessary for verification of these results. As I told you, here are also the performance profiles of the different problems, of the different accuracies, different performance measures. And those are the references used. So thank you very much for watching and listening. I'm open for all your suggestions. Feel free to leave a comment down below, and thank you for listening. Have a nice one.